Hello everyone and welcome to our presentation. We are from Group 1 and today we are going to explore the contribution of vibration studies towards sustainable development in industrial application. When we think of vibration, we are often define it simply as a cyclical back and front movement of an object about an equilibrium position. It is a fundamental mechanical phenomena observed in almost all physical structure under dynamic loading condition. The sources of this vibration are diverse, ranging from natural forces like wind and earthquake to mechanical operations like rotating equipment and unbalanced rotor. However, vibrations mechanics is not just a technical discipline. It is a gateway to sustainable industrial practice. By understanding how systems oscillate, we can design solutions that prevent structural fails, extend the lifespan of critical machinery, and reduce energy waste. This means that integrating vibration knowledge lead directly to a cleaner and more efficient industry. To understand why mitigation is so important, we must look at the dangers on resonance. Resonance occurs when an external force frequency perfectly matches a structural natural frequency. When this happens, the amplitude spike and vibration grow uncontrollably. This causes material fatigue, weakening structural component over time, and can lead to catastrophic structural failure. A tragic historical example for this is the collapse of the Tacoma Narrow Bridge in 1940, which was destroyed by wind-induced resonance. To prevent such disaster, engineers model 1 degree of freedom system using key parameters like mass, m, and stiffness, k. These parameters determine the natural frequency through the formula omega n equals to surd k over m. While damping and damping ratio, damping dissipate vibrational energy. The damping ratio is calculated as zeta equals to c over 2 surd km. A ratio less than 1 is underdamped, equals to 1 is critical damp, and greater than 1 is overdamped. Optimal damping minimizes resonance risk and energy waste. And the behavior of this system is guided by the equation of motion m x double dot plus c x dot plus k x equals to f sine omega t t. While m represents mass, providing resistance to acceleration, k represents stiffness, which act as the resorting force, and c is the damping coefficient, which control energy dissipation and amplitude decay. By utilizing damping, we can dissipate vibrational energy over time, causing the amplitude to decay exponentially and minimizing the risk of resonance. In industrial settings, the machinery is consistently subjected to sources of excitation, such as rotating unbalance in motor or harmonic force from stamping pressures. This is where the concept of engineering isolation becomes critical. Vibration isolator, like spring and viscous damper, are placed between a source and its surrounding to shift the system natural frequency away from excitation frequencies. This protects the structure by absorbing and dissipating vibration energy, which also significantly limits noise pollution in industrial environments. To measure how effectively an isolator works, we look at transmissibility, TR, which is the ratio of F transmitted to F applied. Effective isolation is successfully achieved when the frequency ratio omega over omega n is greater than surd2, dropping TR below 1. By properly managing damping, we avoid the extreme force amplification of undamped resonance and keep the system in the optimal isolation zone. So, how does all of this impact sustainability? The data is clear. Proper vibration mitigation significantly extends machinery service line. Isolated system maintain over 90% performance reliability over a 10 years period. In contrast, unmitigated system begin declining by year 3 or year 4, often experiencing critical failure by year 5. Implementing proper damping reduce maintenance costs up to 40% over a decade. Because of this direct impact, vibration control closely aligns with global sustainability targets. In support SDG 9 Industrial and Innovation by enabling smarter, more resilient industrial infrastructure. It's aligned with SDG 12 Responsible Consumption by extending machinery lifespan and minimize material waste. It's driven SDG 13 climate action by preventing parasitic energy loss and lowering carbon emissions. To close, we must recognize that vibration isolation is not merely an option for comfort. It is a fundamental engineering necessity. The future of sustainable industry is built on the science of vibration, engineered for people, the planet, and progress. Thank you.